This is AP Chemistry, Hoover High School, and this is Lesson 8, Covalent Bonding. So on the last lesson, we learned of one of the three major types of bonding, that's ionic bonding. Now we're going to learn another covalent bonding, and you will be dealing with the covalent bonds virtually every day for the rest of this class. So covalent bonds occur when two or more atoms share electrons. If you recall, ionic bonds, one atom passes an electron completely over to another atom, and then the positive and negative ions, cation, anion, attract each other. In covalent bonds, the two atoms share electrons. One atom does not entirely pass electrons to another. Covalent bonds occur primarily between nonmetals. Those would be the elements in the upper right-hand corner of the periodic table. That would include carbon, nitrogen, oxygen, phosphorus, hydrogen, which is in the upper left-hand corner, but it's a nonmetal, sulfur, and chlorine, and others. Covalent bonds produce combinations of atoms called molecules. Ionic bonds do not form molecules, and we'll talk about the difference between the formula units that ionic bonds form and molecules that are formed by covalent bonds. Finally, covalent bonds are the bonds that are found in you and other living organisms. So just remember, covalent bonds share electrons. The key word is share. So when nonmetals bond, they pull on each other's electrons very hard because they both have high electronegativity. So look at those elements over there in green. Those are the nonmetals. And we know that the upper right-hand corner of the periodic table has high electronegativity. They really like to pull electrons in from the outside. That is to say, electrons that belong to other atoms. They both also, since both have high ionization energies, they don't easily give up electrons. So these elements like to pull in outside electrons, but they're very strong about holding on to their own electrons. So when you have two of these elements bonding, it's like two strong guys having a tug of war. They're both pulling on each other's electrons, but neither one can pull the electron away from the other because they both have high ionization energies. High electronegativity means they both pull on each other's electrons very hard, but they can't win. They can't pull them away from each other because they both have high ionization energies and don't give up their electrons easily. Consequently, the two atoms just agree to share the electrons. So there you go. You got two strong guys over there. They're pulling on each other's electron, but neither one can win the battle, so they end up just agreeing to share the electrons. The octet rule. Now this is a key rule in chemistry. You don't need to understand why the octet rule works, you just have to understand what it does and what its effect is. All of the science behind why atoms like to form octets, again, is beyond the scope of your need to understand, but understand how the octet rule works. So the octet rule says that atoms are most energetically stable. We kind of use the metaphor happy when they can fill their valence orbital. So atoms want to fill their valence orbital. Octet means 8. It's called octet because elements in the second period, that's rho, and below need 8 electrons to fill their outer orbital. So this is an oxygen atom. I should have said atoms in the second period and below. This is an oxygen atom. You'll notice that it has 6 valence electrons, that's electrons in the outer shell, but it also has 2 empty spaces. So oxygen has 6 electrons in its valence orbital. To be happy, oxygen would like to fill the 2 empty spaces. But how? How does it do that? So the octet rule says that atoms are most energetically stable, happy, when they can fill their valence orbital. Octet means 8. It's called octet because elements in the second period, rho, and below need 8 electrons to fill their valence outer orbital. Now the first row is the only exception to that. It's hydrogen and helium, and it only can hold 2 electrons in its valence orbital. So it's still called the octet rule, but in the case of hydrogen, hydrogen can only take on one more electron to fill its valence orbital. So that space right there, hydrogen would like to get an electron into that space. Hydrogen's valence orbital can only hold 2 electrons, so hydrogen needs 1 electron to be happy and fill its valence orbital. So how does it do that? And note what I just said. Even though hydrogen's first orbital can only hold 2, not 8 electrons, it's still called the octet rule. The main idea is that an atom wants to fill its valence orbital to be happy. So each hydrogen shares its electron with oxygen. This gives oxygen a total of 8 valence electrons, so oxygen is happy. Also, oxygen shares an electron to fill the valence orbital of each hydrogen, so the hydrogens are happy. So we take that, we put those 2 together. We take that away and we put those 2 together. So those are the shared electrons. Neither hydrogen could pull oxygen's electron away from it, nor could oxygen pull either hydrogen's electrons away from it. So they agree to share. And why do they do that? Because they both have relatively high ionization energies. They don't give up their electrons. On the other hand, they do want to pull on in outside electrons. And so since they're not capable of pulling electrons away from each other, they just come together and share electrons. So those are the shared electrons. Now notice that what you're doing is you're double counting. If you look at the hydrogen at the top, the atom at the top, it has 2 electrons, one which it originally owned and the other which oxygen shared with it. So that counts as 2 electrons for the hydrogen up there on top. However, those 2 electrons also count as 2 electrons for the oxygen atom. Similarly, the one on the right, the hydrogen on the right, it gave 1 electron, it shared 1 electron, oxygen shared 1 electron. So those 2 electrons over on the right, they count for hydrogen as 2 electrons for hydrogen, but they also count as 2 electrons for oxygen. So in other words, you're double counting those shared electrons. So all oxygen knows is, it doesn't know whether it's sharing or not. All it knows is it's got 8 electrons in its valence orbital and it's happy. All each of the hydrogens knows is that they have 2 electrons in their valence orbital, so they're both happy. Because 2 hydrogens fill the valence orbital of oxygen and oxygen fills the valence orbital of the 2 hydrogens, this combination creates H2O, or water. So these electrons are double counted. They both belong to the hydrogen atom, and at the same time they both belong to the oxygen atom. Similarly, these electrons are double counted. They both belong to the hydrogen atom, and at the same time they both belong to the oxygen atom. The bonds created between nonmetals by atoms sharing electrons according to the octet rule are called covalent bonds. Think of what that word means. Valence means valent means the valence orbital, and co means together. Like when you cooperate or a co-pilot on a plane, it means things that are working together. So they're covalent. They share their valence electrons. So remember, covalent bonds share. A diatomic molecule is a bond between 2 atoms of the same element. Diatomic molecules are the most common covalent bonds in nature. There are 7 diatomic molecules. 4 of these are halogens with 7 valence electrons, and they are hydrogen. So these are all of them. Hydrogen is not a halogen, but one of them is hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. In other words, anytime, we talked about this earlier, anytime you find hydrogen in nature, it's not a hydrogen atom. It's a hydrogen molecule with 2 hydrogen atoms stuck together. Same with nitrogen. The oxygen we breathe is not oxygen atoms, it's oxygen molecules, 2 oxygen atoms bonded together, covalently bonded together. So in nature, these 7 elements you will always find as molecules, 2 atoms bonded together. You'll never just find a bromine or an iodine all by itself. So these elements always form a diatomic molecule when they are in gas form. So covalent bonds happen between two nonmetals. Nonmetals have high ionization energy and high electronegativity. They're both strong guys. So they have high ionization energy, meaning they don't give up their electrons easily. It's very difficult to take an electron away from a nonmetal. On the other hand, they have high electronegativity, which means they're very good at taking electrons away from other atoms. So they're strong guys. Both nonmetals pull hard on the electrons of the other atom, but both do not give up their electrons easily. Since neither atom can win the tug of war, they decide to share electrons in a way that they both fulfill the octet rule by having a full valence orbital. Sometimes this will lead to double and triple bonds. We'll talk about that shortly. And finally, if one of the atoms has higher electronegativity, it will pull all of the electrons closer to it, creating a polar covalent bond. And we'll talk about that more. Basically what that means is, even though they're two strong guys and neither one can win the tug of war, one of them will be probably a little stronger than the other, and it can't totally take the electrons away from the weaker one, but it can kind of pull all the electrons towards it. That means the side of the molecule that has the strong guy, the stronger of the two guys that's pulling the electrons, will be more negatively charged, and the other side will be more positively charged. And we'll show examples of that later. And here's the example. This is because oxygen in water is a polar molecule. And this is a water molecule. It has two hydrogen atoms up at the top and an oxygen atom down at the bottom there in the blue. So this is because oxygen is more electronegative than hydrogen, so it pulls the electrons toward it. The water molecule below is polar. So this side of the water molecule contains two hydrogen atoms. That's two protons. The red rectangle has a charge of +2. So I've drawn arbitrary boxes around these. And you're seeing that in the red box, all you have are two protons. Those are the nuclei of the two hydrogen atoms. So the electrons, because oxygen is more electronegative than hydrogen, the electrons tend to get pulled over towards the oxygen and away from the hydrogen. They don't get totally taken away from the hydrogen, they just tend to be pulled in that direction. So you'll notice in the red box you have two plus signs, two little circles with plus signs, the nucleus of the hydrogens, and no electrons. So that means inside that red box, if we just isolate that area, that part of the molecule, that it's positively charged. This side of the molecule contains 8 protons. Those are from the oxygen atom. The blue rectangle has a charge of 8 minus 10, or 2 minus. In other words, you can count that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in the blue box, and 8 protons, which are in the nucleus of the oxygen atom. That means the blue side of the molecule has a negative charge. It has a 2 minus negative charge. So the top side of that molecule, the red, is positively charged. The bottom side is negatively charged. But what you should notice is that a water molecule is electrically neutral. It has a total, if you look at all of the protons, 8 in oxygen and 2 more in each and 2 in the hydrogens. It's a total of 10 protons. And it also has 10 electrons. 10 and 10 is electrically neutral. It's just that the electrons are pulled over to one side, so that side of the water molecule is a little more negative, and the red side, the hydrogen side, is a little more positive. So that's called a polar molecule because it has 2 poles, a plus pole and a minus pole. A polar molecule is an electrically neutral molecule that has a positive side and a negative side. This means that it acts like a magnet when other polar molecules are nearby, so it will be attracted to other polar molecules. Covalent bonds form molecules. These H2O water molecules, for example, are separate structures from all other water molecules. When water boils, the water molecules separate and move freely, so they can move apart from each other. You can think of them like 2 cars. So think of molecules as cars that can move independently of one another. So we talked about ionic bonds, we talked about formula units, but they weren't separate structures. They were like apartments in an apartment building or bricks in a wall. You could tell one formula unit from the next, but they were stuck together in a big block. Whereas molecules are actually separate independent structures that can move apart, as you just saw in this illustration. So ionic bonds form crystal lattice structures. Table salt, sodium chloride, has a formula unit of NaCl. There is one sodium atom for each chlorine. So the blue chlorine, just take the chlorine that's blue for an example. The blue chlorine atom is attached to 4 sodium atoms. It doesn't belong to any one sodium atom. Even though there's one sodium for every chlorine, that chlorine doesn't belong necessarily to any one sodium. It's bonded to all 4 of them. Similarly, the next sodium chlorine over is bonded to the 4 sodiums around it. Similarly, the sodium that's kind of in the middle there is bonded to the 4 chlorines that are around it. So even though there's a one-to-one correspondence, which we call NaCl, meaning 1 Na for every 1 Cl, it's not that Cl belongs to any one sodium there, or the sodiums belong to any one chlorine. NaCl is called a formula unit or unit cell because it identifies that there is one sodium for each chlorine. A formula unit is not a separate structure in the way a molecule is. These are like bricks in a wall. You can't just pull one out. So there's the chlorine in blue, and you can see it's connected to all 4 of those sodium atoms around it. A formula unit defines the smallest basic unit of a crystal lattice structure, but it is not a separate structure. But if you took the formula unit, NaCl, so you see 1 Na and 1 Cl in that red box, and you repeated it over and over again, that would create the entire structure. So again, it's like if you take the formula unit is like an apartment in an apartment building. An apartment can be distinguished from other apartments, but it's not a separate structure that can move independently like a car. But if you took one apartment and just kept replicating it and putting them side by side and on top of each other, you'd basically then end up with the apartment building. Okay, Lewis dot structures. Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and valence electrons. So here's a beryllium atom, and we've diagrammed an atom before. It has 4 protons. The most common isotope has 5 neutrons, and since it has 4 protons, it also has 4 electrons. 2 of them in the first orbital, and then the other 2 will be in the second orbital, spread out like that. So a Lewis dot structure is simple to make. Write the atomic symbol, so for beryllium it's Be, and then you draw only the valence electrons around the atomic symbol. So there's 1, and there's 2. And that's the Lewis dot structure for beryllium. Again, it identifies the element, and then it shows where the valence electrons are located. So Lewis dot structures show only valence electrons, since only these electrons are involved in chemical bonds. Let's look at another example. See if you can do this one on your own. Here's oxygen. So write the atomic symbol. There it is. And draw only the valence electrons around the symbol. And there we go. That's the Lewis dot structure for oxygen. One more. Phosphorus. Write the atomic symbol. Now you notice phosphorus has 3 orbitals. Doesn't matter, you're only interested in whatever that outermost orbital is. So draw only the valence electrons around the symbol, so those would come from the 3rd orbital. Okay, and that's the Lewis dot structure for phosphorus. Now you may say, so what? You just had a simple way to draw an atom. Believe it or not, you will find out you can do some very sophisticated analysis of molecules and of covalent bonds using Lewis dot structures. So it seems trivial what we just did, but it's actually, you're going to see, we're going to put these to use in a very short time. Okay, so Lewis dot structure representation of a water molecule is shown here. All atoms want to fill their valence orbitals. Oxygen agrees to share one of its unpaired electrons with a hydrogen if hydrogen shares its electron with oxygen. Notice that this bond is taking place on the side of oxygen that has unpaired electrons. If electrons are already paired, the top pair and the right side pair on oxygen, then you can kind of think of them as they're already married. They can't pair up with anybody else, and so you have to do this with unpaired electrons. So right there, this one comes over and they share their electrons with each other. Oxygen repeats this process with another hydrogen right there, and this one comes up and shares. Both hydrogen atoms and oxygen end up with filled valence orbitals, creating a covalent bond and fulfilling the octet rule. Covalent bonds form molecules. So that's a water molecule. It's a separate structure. Just remember, when you boil water, the water molecules start floating up as steam up above the pan. So they break apart from each other and they form separate, they can form separate independent structures called molecules. Okay, a diatomic molecule is a bond between two atoms of the same element. Diatomic molecules are the most common covalent bonds in nature. There are 7 diatomic molecules. 4 of these are halogens. So we already talked about this. So we're just seeing an example. There's an empty space on fluorine. There's another empty space on another fluorine. Those are 2 empty spaces. And they come together. And now you'll notice that each of the fluorine atoms has a full octet around it, and those are sharing the two middle electrons for a covalent bond. Each oxygen atom below has 6 valence electrons for a total of 12. How can we create 2 octets from 12 electrons? So think about that. Each of those valence orbitals, those second orbitals, have to have an octet. That's 8 electrons. But if you look at the 2 valence orbitals, you count 6 electrons in one atom and 6 electrons in the other atom, just the valence orbital, just the outer orbital. That's a total of 12. So how can you get 8 plus 8 or 16 if you only have 6 plus 6 is 12? How do you do that? Think about this, okay? It's a little thought puzzle for you here. I'll give you a hint. They can share more than just 2 electrons. So think about that. If you want, you can pause and think about it for a little bit, and then I'm going to continue on. Okay, so I'm going to continue on. I'm going to show you how they can form 2 octets where each atom has 8 electrons, even though they only have a total of 12 electrons in their valence orbital. And there it is. So each oxygen shares both of its unpaired electrons to form what is called a double bond. Notice that each oxygen atom has 8 electrons in its valence orbital because the electrons in the yellow area are counted for both atoms. So if you take the one on the left, you see 4 valence electrons over on the left-hand side of the left atom, and then you see those 4 electrons in the yellow. They count as belonging to the atom on the left. So that's 1, 2, 3, 4, 5, 6, 7, 8. Similarly, the atom on the right, it has 4 valence electrons over on the right-hand side, and then it has those 4 electrons in yellow as well. They count for the atom on the right. They're double counted. So it has 8 electrons as well. So that's called a double bond. Double bonds are stronger than single bonds. They're also shorter. They hold the atoms closer together than a single bond does. So Lewis dot structure for an O2 molecule looks like this. Just what you saw before, except you've drawn it in Lewis dot form. So in a covalent bond, electrons that bond 2 atoms are called bonding electrons. So that's a term you should know. The electrons that do not bond to 2 atoms are called non-bonding electrons or lone pair electrons. Those are terms you should know as well. A pair of bonding electrons can be represented by a line. Lines should not be used to represent lone pairs. So each line represents 2 electrons. So you have 4 electrons in between the 2 oxygens, and then the outside electrons, those lone pair electrons on the outside of each of those atoms, you do not represent those with a line. You represent them as dots. Okay, carbon dioxide, CO2, is what you exhale when you breathe. How does carbon dioxide bond with 2 oxygens? So there's a total of 16 valence electrons between the 2 oxygen and the 1 carbon atom. So count them. You've got 6 on the oxygen, 6 on the other oxygen, plus 4 more on the carbon. That's a total of 16. And yet they all have to end up with an octet. That's 8 and 8 and 8. That's a total of 24. So how do you turn 16 valence electrons into 24 valence electrons? Well, you do it like this. So by creating double bonds between the carbon atom and each of the oxygen atoms, octets can be formed around each atom. Carbon forms double bonds with each oxygen. This provides octets for all 3 atoms. So you'll notice, let me go back to that. You'll notice that oxygen on the left has 8 valence electrons. Carbon has 8. It has 4 on one side and 4 on the other. And the oxygen on the right has 8 valence electrons. And so that forms, those form 2 double bonds. And this, by the way, carbon dioxide, is a non-polar molecule because the oxygens are having a tug of war basically with each other. The carbon is in the middle, but the oxygens are having a tug of war with each other. So the oxygen on one side is not going to pull the electrons over to it any more than the oxygen on the other side. Therefore, the electrons and the charge is going to be equally balanced along the length of that molecule, and that's going to be a non-polar molecule. It doesn't have a positive side and a negative side. Usually when you have a molecule that looks symmetrical, it looks balanced like this, it's going to be non-polar. When you have a molecule that looks lopsided, like a water molecule where the hydrogens are over on one side, then it's going to be polar. That's generally the case, just a simple rule of thumb. Okay, and the Lewis dot structure of a carbon dioxide can be drawn with a line to represent a pair of bonding electrons, just like we did in the previous example. Carbon dioxide, CO2, has a balanced charge. The 2 oxygen atoms pull on the electrons equally, so the charge is equally distributed. When electrons are not pulled to one side of a molecule, the molecule is nonpolar. Finally, we're going to just touch on metallic bonds. A metallic bond, electrons are attached to the protons in the nucleus, or attracted to the protons in the nucleus, but the electrons are not held closely. Think of these as the transition metals, which are kind of low down on the periodic table, so they have a lot of orbitals. If they have a lot of orbitals, their valence electrons aren't held very tightly. They have low ionization energies, but they don't get ionized typically. They do, but in the case of metallic bonds, they don't totally get ionized. They just end up sharing electrons among the entire group of atoms. So electrons are not held closely to any particular atom, so they jump from one atom to the next when they are pushed. So copper, abbreviation Cu, has low ionization energy, so it easily passes electrons from one copper atom to another. The yellow copper circles represent the nucleus of the copper atom and the core electrons. The blue circles represent the valence electrons, those outer electrons. So you see, they're not permanently ionized from one atom to another. They just keep jumping around between the atoms because they're not tightly held to any one atom. And that creates this constant plus minus charge throughout the metal and throughout the metallic bonds. And what that does is it causes the metallic bond. That's what causes metal atoms to bond together. So this is called the electron sea model because the electrons move around like fish in the sea. Okay, here's some characteristics of ionic and covalent bonds. So first, the unit. Ionic bond has a formula unit which builds up. It just repeats itself to form a crystal lattice structure, like an apartment building or like bricks in a wall. The covalent bond forms an independent structure called a molecule. Bond formation in ionic bonds results from passing electrons from one atom to another, creating an anion and a cation, which attract each other. Covalent bonds are two strong guys. They can't pull electrons away from the other guy, so they decide to share electrons. Elements involved. Ionic compounds are metals, which are the weak guys, and nonmetals, which are the strong guys. In covalent bonds, it's two strong guys. That's two nonmetals. Physical state. Ionic bonds are generally as solids, whereas covalent can be solid, liquid, or gas. Just think of water. It can be ice, it can be liquid water, it can be vapor. Melting point are generally higher in ionic compounds than covalent compounds. Generally above 300 degrees centigrade, below 300 degrees for a covalent bond. Maybe you did a simple experiment. Sometimes I have my students do it near the beginning of the year, where they put a little tinfoil cup, and they put salt in one of them, and then they make another tinfoil cup, and they put sugar in that, and they hold them both over the flame, and what they find is that the sugar melts. It turns brown and eventually black, and it melts, whereas the salt, which is an ionic compound, NaCl, does not melt. So ionic compounds, just remember that example, sugar versus salt. Sugar melts, salt doesn't. So ionic compounds like salt have a higher melting point than covalent compounds like sugar. Solubility in water. Ionic compounds have high solubility generally. Think of salt, it dissolves in water. Covalent bonds have low solubility in water. And that's a good thing, because your body is 70% water. And I told you earlier that your body is made up of covalent bonds of nonmetals covalently bonded. So if they dissolved in water, you would dissolve. So covalent bonds, keep that example in mind. Your body is non-metallic covalent bonds, and obviously it doesn't dissolve in water because you have water all inside of your body. And finally, conductivity. Conductivity means both electricity and heat. Ionic compounds generally conduct electricity and heat well. Covalent bonds don't. Another little project we will do in class when we come back to school is we'll have a beaker of salt water and a beaker of sugar water. And you can actually light up a light bulb by putting two electrodes into the salt water because it conducts electricity. But you put them into the sugar water, it won't light up the light bulb because covalent bonds don't conduct electricity well. Okay, so that takes care of our lesson on covalent bonds. So you've learned really all three of the major types of bonds. Again, I find it amazing that every substance in the universe is put together by 90 atoms, and there's only three ways you can put them together: ionic bonds, covalent bonds, or metallic bonds. And really, metallic bonds are kind of a side issue with us. What we're going to talk about throughout this course really is ionic and covalent bonds. Okay, so that takes care of that. Next lesson is lesson 9, and we'll do a few general things in that one, and then we will wrap up our foundations unit for AP Chemistry.